So this is quantum generative adversarial networks. And that's going to be a tough one. The reason I'm doing that is because I've been reading some of the comments and some of the feedback that I've gotten from people. And basically, it seems like not everything that is in the machine learning realm really has any advantage over their classical counterparts in terms of the quantum versions of them. And then I remember reading that GANs is one of the places where we still theoretically there's no proof that, or still theoretically believe that they are significantly better than their classical counterparts. And so I picked just randomly this paper. I quickly scanned it and I saw that there was probably illustrative enough to kind of try to break it down. Although, again, I had to refresh a lot my knowledge on GANs, but it's the introduction here is pretty explanatory, pretty good, well done. And then I think basically what this is trying to do is, so you've got your generator and your discriminator. So you're basically training two different models. One of them is trying to kind of make fake stuff, and the other one is trying to figure out whether it's fake or it's real, right? So it's sort of and this is really generic. That's why I think it's going to be complicated to make something practical out of this, and it's probably take 3 or 4 videos, but I'm going to be limiting them to 30 minutes each. So I kind of force myself to go back and then kind of compartmentalize my learning experience here. And in this first video, I want to just fly over the paper and then try to see if there's any thing that we can start working on, or there are different parts we have to understand, or any other basic knowledge we need to first gather. Because I assume that at the end of the day, the way you implement those models can be in many different ways, and this is an assumption, right? So the GAN concept is just the overall the overarching concept, which I'm not so sure what can a quantum version at that level bring in terms of in terms of an advantage. So I'm gonna skip this, but this is the idea, right? So and let's get just going. So it's gonna be probably a bit bumpy this first session, but bear with me. So first, probably a high-level overview of the GAN architecture and figure 4. In paper 4. Suppose the raw data comes from the distribution generated by some potential process. We'll normalize. Okay. Figure 1. In A, we show the building blocks of classical GANs. A discriminator must determine whether the samples it is given are produced by a real source or a generator with whatever noise Z. I guess this is used to then kind of make the generated data look a bit more real. So we generalize the idea of for the quantum setting. So for a quantum case, suppose that we're given a data source R, which given a label, I think it's lambda, outputs a density. So this is the first time that I see a paper using a density matrix. I'm not. It's not that I'm reading a lot of papers, but it's because you can check out the other videos that I'm working on in terms of density matrix and its utility. Here it seems like they use it, but I don't know exactly what for. The general aim of training a GAN is to find a generator G which mimics the real data source R. In the quantum case, we define G to be a variational quantum circuit. I think I remember reading something about this, but I'm not so sure. I remember there's a block of, because I got some interesting variational quantum circuits. So I remember David Kopchik, exactly. I think this is because I remember he had a really interesting blog touching quantum computing and machine learning. I found this out through the Warsaw Quantum Computing Facebook group. So what is a variational quantum circuit? It's after reading it's possible. Okay, rational. A family of hybrid quantum classical algorithms. The ingredients of rational. Okay, so a parameterized circuit. Okay, from the output from the quantum circuit, and then a learning algorithm. Okay, so this is basically another way to say it's this setup where we have a quantum circuit that has some parameters, and then an output, and then that's the traditional, you kind of whatever learn and then adapt the parameters of this circuit. So, and then you measure again. So that's just, I guess, the basics. But I highly recommend, I'm not going to go into the details here, but I highly recommend you guys check out this blog because there's quite some interesting stuff and it's pretty practical. So the parameterized can decompose the unitary. So this is just an example. Okay. Architecture. So this would probably be a block where we encode the X onto the zero, onto the ground state, so to say, and then we do different stuff. Okay. Okay. Yeah. Not gonna dive into this, but it's definitely really useful. Definitely really useful. So all what this is saying is it's going to be it's going to be a circuit that we're going to be adapting based on the output, and then we're going to be running it again. So this is the traditional setup for any learning algorithm. Where's the quantum state? I'm skipping the math for now. I always get hit by that, but the role of the extra state is twofold. On one hand, it can be seen as a source of unstructured noise, which powers entropy. For instance, we could have a generator which is unitary, producing a fixed state for each lambda and z. By allowing the input z to randomly fluctuate, we can create more than one output state for each label. On the other hand, the variable z can serve as a control for the generator. I guess this is just going to be, because I see here a circuit that it's sort of a high level, and I think that's the that seems to be sort of a circuit version of this here. Let me see, because it says the general structure of QGANs, the real source R or the parameterized generator. So this is the generator is applied. Okay. And this is the density matrix. Uses the information. Okay, so it's using the density matrix, but it doesn't know whether it's from the real set or from the generated set. What is that? Define the out D, path D, and label D. I don't know, but I guess that's the label thing. The discriminator D uses the information in the matrix, in the density matrix from the source and initial resource state. Okay, 0, 0 lambda. Okay, so that's kind of like an initial state. Because that's the same label. Because the discriminator needs to know this, and then it needs to, whatever it does inside, figure out whether this density matrix could be a real thing or not, could be is correct or not, or is fake. Okay. And I guess then that's fed back to the generator to try to fake it better next time. So this is something we could definitely construct. R or G. So this is something we could definitely construct by first kind of doing two subroutines. So I'm gonna call one RG, and then we're gonna make another one called D for the discriminator D. So I'm gonna just first, because I'm not quite sure, this here doesn't seem to be logically or at a quantum circuit level something you can do, because we're talking about qubits and then now suddenly it's a density matrix. But kind of okay. So you've got 1, 2, 3, 4, 5, 6. Okay, subs. This is not just a 0 qubit, it can be many, right? And this is many as well. But for the sake of the example, let's put 1, 2, 3, 4, 5, 6 qubits. 6 6 qubits. And so this one has 1, 2, 3, 4, and this one has 3 inputs, right? So Q1, Q2, Q3, Q4. I'm gonna probably then rename them for Q2, Q3, something a bit more readable. But the idea is you first do the other way around. So this is just Q3, and then this is D. D needs 4. So first is RG at the bottom, and then it's like this, and then it's a measurement. Okay, let me save that. It's really, I don't know. Then we'll see. Maybe that was useless, but maybe then we can just break these things down and actually implement some interesting. This is I'm a bit afraid of this because it seems like it's not something you can implement directly on the circuit if this is really using the density matrix. But let's see. Maybe they have. Okay, so blah blah blah. Real fake. The quantum cost function, I'm going to skip that. So basically, I guess this is how they define whatever thing is going to be minimized. That's kind of, at the end of the day, what you do with any learning algorithm. You're going to maximize something or minimize something, right? And then, that's going to be a tough one. Again, this first part is just the bird's eye view. But I'm trying to stay at the intuition level, so I'm not gonna. And I might make some mistakes, but I'm not going to dive into all the mathematics for this for the purpose of this. It's not what I'm trying to do. What is quantum gradients? A key element of GANs is that the generator can be optimized by using gradient signals obtained from the discriminator. Machine learning gradients. What is this? Machine learning gradients are used in gradient descent. We often have a loss function, and we try to do this by following negative of the gradient of the function. The gradient is a vector. Introduction to gradients. So basic concepts, blah blah blah. Okay, I think this is partials function. It seems this is something like that you're calculating in which direction the function is kind of going down, and that's your gradient, and then you basically move in that direction because they're using the derivatives here. So partials fxy, okay, which is basically that's what it's doing here. Okay, so I'm going to assume this is this, and this is a quantum version of it. So this probably will require its own video. A key element of GANs is that the generator can be optimized by using gradient signals obtained from the discriminator. Thus, in addition to quantum circuits for GND, we would also like to have quantum circuits which can compute the required gradients. Boo, a lot of related papers. So, really? What is... Isn't there a shorter introduction? Oh, cheat sheets. I like them. Okay. Yeah, that's what I thought. That's what I thought. So we've got a cost function, and then there's like a gradient. Okay, so basically, I guess what it's trying to say is whatever the existing model or the quantum version is the discriminator, then we can see try to calculate the gradient, so then we know how to tweak the input. It's all pretty abstract, but I think that's what it's trying to do. Start. Flip coin tails. We illustrate the algorithmic flow of the training of a GAN. See text for details. Okay. Oh, okay. Some interesting stuff. So basically, they go ahead and they explain how In particular, other approaches for using a quantum computer to compute gradients of quantum circuits. Oh, it's interesting. Gradients of quantum circuits. That probably is something we can then dive into, and that might be even helpful. Okay, I see here there's a lot of maths, but it's like probably skippable. Sorry. Okay, so here it's I think there can be a way you can read a paper just by reading the descriptions in the figures. In A, we show the general structure of quantum gradients and the structure of quantum Hessians. What is quantum Hessian? Quantum Hessian. Hessian matrix. In mathematics, a Hessian matrix is a square matrix of a second order. It's going to be a tough one to break down. I guess Hessian matrices or Hessian whatever we probably have to explore later on. So I'm guessing this is the way we're going to approach the problem. So okay. But I see. So it's basically, I think it's using these to using quantum gradients to train. Okay, so it's using the quantum gradients to actually train and then figure out what's the best next parameters for the algorithm. But that training, it's done not in the quantum computer. Okay, here you go. I'm just literally taking a look at the figures, you know. Okay, so that's kind of okay. So they've transformed this. They have transformed this D into these, whatever those things are. And here we see some fancy stuff. In terms of a controlled whatever this is, and okay, and so this is supposed to be you're supposed to measure the gradient. Okay, so that's an additional qubit in here. So there's an additional qubit. There's an additional qubit. There's an additional qubit, which is going to be the gradient, which means this one goes. Why doesn't this go? Come on. We said RGD, and so this is going to be the gradient. That's what we kind of measure. I mean, I don't know if this is just a separate circuit or okay, but we have to break this down. And this is probably going to be the funny or the interesting stuff, but I still don't see what's the quantumness advantage here. Practical Ansatz. Is this a real English word? Because I know German Ansatz is approach, but is this a real English word? An assumption about the form of an unknown function. What? It's an actual mathematical term? An assumption about the form of an unknown function which is made in order to facilitate solution of an equation to another problem. Mind-blowing. A potentially useful answer to parameterize this is shown in figure 7. Yes, that's what I want to. No, okay. Oh, interesting. So that's like okay, so it's implemented with rotations, I guess. Don't know if it's really doable with the IBM Q experience, but it seems like they've gone that far to make a complicated, okay, conclusions. So let's read the conclusions. Quantum machine learning is likely to be one of the first general purpose. We showed how generative models can be trained on quantum computers. We have reformulated the blah blah blah. Yeah. Finalization of the QGANs can be trained and practiced from. Here you go. It is expected that QGANs will have a more versatile representation power than their classical counterpart. What does this mean? For example, we can speculate that a large enough QGAN could learn to generate encrypted data labeled by RSA public encryption keys, since quantum computers have the capacity to perform Shor factoring and hence decryption. In that case, the optimal generator would learn a statistical model of the unencrypted data for each key and encrypt with the label. Each key and encrypt with the label. Other classical cryptographic systems, such as elliptic curve, could also be vulnerable to this type of attack. Okay, so I think the quantumness here is basically in the fact that let me put it this way: the stuff you can do within the generator is far more powerful than what you can do with a classical generator. I think that is the idea, and probably it's also the reason why this hasn't been proved, like that it's not true or something, because basically you can do fancy stuff, right? So the space that you can, and because, and that's maybe the reason why they're using the density matrix here also, like whatever you can express, it's far more complex, right? So I think what they mean by this thing with the Shor algorithm, which I'm going to work on basically really soon, is that you can basically you can maybe create a G, so like the faking model, uh, to actually learn the patterns of the encryption or something like that. I don't know. I'm probably talking BS, but I think the quantum advantage here is in the power in using a quantum circuit to it basically it's in using qubits instead of traditional beats. So you can represent fancier and bigger things. Um, I think that's what it means. So probably what we're gonna do next is I'm gonna do another video where we'll recap a little bit this, and where I will first probably try to understand I think it makes sense for me to understand what the um, I'm curious about this gradient stuff, because I think that's in general helpful for other machine learning and AI stuff. So I'm going to see if I can do another video just on this, on how to implement those gradient things, and or what's the intuition, what's the intuition level, what's going on there, because at the end of the day, what happens inside the boxes, what happens here inside, right, and this RG circuit. I mean, I don't know if it doesn't seem like the paper covers that. And probably it depends on, it really depends on the problem you're trying to solve with your GAN. You're going to generate things in a different way. And that's going to be, so, I probably can't explore that a lot, but I can definitely take a look at the gradient stuff. I think that's going to be useful for our intuition. Maybe if I check out some of the related papers, I find some interesting examples of what a G function could be. Or a G circuit could be. Maybe that's an interesting one. Cool. That looks super exciting. Like it looks like really promising. It's complex, but it looks promising. But at the intuition level, it's simple, right? So you've got like a circuit that generates something, and then you've got another circuit that tries to figure out whether it's whether you've just faked it or used an actual real representation, and then by calculating this gradient thing, you use that to train outside of the quantum thing. You basically train and try to optimize the parameters of your circuit, so that at the end they get the goal, I guess, is to get a model that is really good at generating whatever you're trying to generate. Yeah, I think that's cool. Perfect.